Hello and welcome to the channel. This is the third episode of the tutorial series which is COMSOL Multiphysics for beginners. So in this episode what we are going to learn is what is numerical solution, then what is finite difference method, and after that what is discretization and meshing. In the last episode what I taught was the various steps in solving a problem using COMSOL multiphysics, and one of the step was meshing, and due to the time limitation of the video I was not able to elaborate the concept of meshing and what are various steps of the meshing, so I thought it needed a separate video. So I am starting from the very basics, from the very scratch, to explain what is meshing and what are various steps of meshing. So let us start the episode. Now, numerical solution. So for example, we have a function, say dy divided by dx, a differential equation is cos x. So we know the antiderivative of cos x exists, we know that, and the antiderivative of cos x is sin x. That means this differential equation can be solved analytically and we can get the solution. Why? Because the antiderivative of cos x exists. So how to solve this? So suppose we apply integration with respect to x. So what we will have is integrate dy over dx with respect to x is equal to integrate cos x with respect to x. So integral differential will get cancelled out, so we have y of x, only y, which is the function of x, which is equal to, and now since we already know that the antiderivative of cos x exists, that is how the analytical solution exists. Antiderivative of cos x is sin x, so we write here sin x plus some integration constant. We will leave that. Our solution is here. Now this solution is the analytical solution. Analytical solution because we were able to convert a differential equation into a functional form which defines the solution of this differential equation at any point. Suppose this is the domain. Suppose this is domain. Say this is x equals 0. This is here x goes to infinity, and this line is the domain of our equation. This is the domain under which our function, this function or our very differential equation is defined. This is its domain. So we got its solution in analytical form, which means if we want to find the value of y at any value of x, we can get it from this functional form of the solution. Now this functional form of any point, there are infinite number of points from this to this in its domain, infinite number of pointers, and at any point in the domain we can find the solution. We can find the value of y just putting the value of x here and solving this analytical solution. So when such a solution exists, we say we solve the differential equation analytically, and such a solution is called a closed form solution. Why? Because in this domain we can use this function to find value at any point. There is infinite number of points, that means value at infinite number of points we can calculate using the function form. So this is a closed form of solution of this equation. But this is not always possible. There are many functions whose antiderivative does not exist. If antiderivative of the function does not exist, that means we cannot solve it analytically. How can we solve such type of equations? This is where concept of numerical solution comes in. Our differential equation is dy by dx is equal to cos of x square. This is now our differential equation, and we want to solve this to get the solution. Now if we see, there is no antiderivative that exists for, there is no function, no algebraic function, no exponential function, no logarithmic function, not any function that exists for this cos of x square. This is a classical example for a function where the antiderivative does not exist. So if we want to solve such a problem, so we know its solution will be y of x equals integration of cos of x square and since there is no antiderivative for this, so there is no analytical solution for this equation. So how to solve this equation and other such type of equations? So we solve such type of equations numerically. We use a numerical solution for such type of equations. Now how? There are many methods that with the help of which we can solve this. Now what's the difference between the two solutions, the analytical solution that we got and the numerical solution that we are talking about right now? So the difference is that solution was available in the functional form, and we could put any value of x to get the value of y at that value of x. At any point in the domain, we have the solution at any point in the domain, not just selected points, at any point. Now, when we solve this function numerically, it will not give us the functional form of the solution. It will give us values at discrete points, and it will give us values in the tabulated form. We will have solution in the tabulated form. We will have like at x is equal to 1, the value is y of x is this. At x is equal to 1.5, the value is this. At x is equal to 2, the value is this. So we will get the solution in the tabulated form. This is the numerical difference between the numerical solution and the analytical solution. And of course, the better one is the analytical solution, because we will have any point in the domain at which we want to find the value of y. But when the analytical solution is not available, so we have no other option but to use this numerical solution, use this tabulated data, and whatever point is in the domain we want to find the solution at, we will get the tabulated values at those points depending upon how we choose the domain. This I will explain it how. Now we know there are some functions for which analytical solution exists, and there are some other functions for which analytical solution does not exist, and we have to use numerical solution, and that solution is in the form of a tabulated functional form, not in algebraic form, not in analytical functional form. So no closed form of solution exists. No closed form of solution exists. Only the we can say the open solution, or the tabulated numerical solution, or the tabulated solution exists for such type of functions. We will take example of finite difference method. I will take an example of finite difference method. I will not go into detail how to solve this particular differential equation using a numerical technique like trapezoidal rule or Runge-Kutta rule or Simpson's rule. Will not go into that because that is not that's not relevant to our video right now. So I want to reach to the meshing. So suppose there's a rod, and one of its ends is at 100 degrees Celsius and the other end is at 20 degrees Celsius. And why we want to know is how the temperature varies from one section to the another section of the rod in this direction. Say this is the x direction. We want to know that. That means, in other words, we want to know what is T of x. And in other words, we want to know what is the temperature distribution throughout the this rod. And we know this, since this is a heat conduction problem, and heat conduction in one-dimensional problem, and there is no heat generation, no generation of heat. So the Fourier's law that governs the heat conduction has this form: minus k d2t by dx square is equal to 0. This is for one dimension and with no heat generation. This is the Fourier law of heat conduction. Now, this is the equation, this is the law where we get the T of x. So that means we have to solve a differential equation, which is a second order differential equation in space, in spatial coordinate. We have to solve this. Again, same, we have a differential equation, we have to solve it. Now this is simple. Analytical solution exists for such type of equations. This is a basic form of the equation. Suppose it is in 2 dimension, still analytical solution exists. Suppose it is in 3 dimension, all the 3 dimensions. So no analytical solution exists. We have no option but to use the numerical solution. Now let us say this is the 1 dimension. We want to find a numerical solution of this 1-dimensional heat equation. Same procedure will be for 2 and 3 dimension as well. So how to solve this? Let us say we are choosing a homogeneous material for which properties stay constant with time as well as with the position. properties stay constant. And the property, one property that we are interested for this problem is the thermal conductivity. Say thermal conductivity is constant. So if K is constant, we can divide both sides by K and or minus K, and what we are left with is d2t divided by dx square is equal to 0, or in other words we write it as t double dash of x equals 0. This is what we get in the simplest form. So this will give us the temperature distribution, but we have this is a differential form. We have to derive the t of x from this t double dash of x. Now how do we do that? I will show the finite difference method, how it is done. Since we know value at this point and value at this point, and we always have a problem differential problem which we want to solve is, if it is a differential equation, it's a one-dimensional differential equation in one variable, then we will be having one boundary condition. We will be having one known value. That means one known value. If it is suppose it's a differential equation in two variables, or if it is a differential equation of second order, that means we will be having two given values. We will be knowing the value of t at two different points. So suppose at this end the t1 value is 100, and at this end t2 value is say 20 degrees Celsius. So we know two values. This is a second order differential equation problem, t double dash of x equals 0. So we can solve it. So differential equation, second order, two known values, we can solve it. Two boundary conditions, we can solve it. So how to solve it is, what we do is we know that the differential equation or any form of differential equation, whether the partial or ordinary differential equation, we cannot apply the differential equation to the entire domain. This is our domain right now. This is, suppose if it is the length of the rod is L, so our x value is L. This is our domain is the one-dimensional length, our domain is one-dimensional, so its length is L. So this is our domain. So we cannot apply the differential equation to the entire domain. Why? Because differential equations are defined for infinitesimally small element. By definition, they are applied to an element. They will be applied to this element whose width is dx, and we will solve it for this element. Then we will apply it to another such element, solve for that. We will apply it to all such elements, solve for all, then integrate and get the solution for the entire rod. So how we do that is, suppose if we know the value of temperature at a value x, which we know, suppose at x is equal to x naught, t value is 100. So if we know the value of temperature at one point, we can find its value at the nearby point. So if we know here, we can find its value at the nearby point, which is infinitesimally near to it, very near to it. So we can find that. We know from the mathematics, there's a theorem called the Taylor series expansion. Taylor series expansion says, if we know the value of a quantity at a value x, we can find its value at the nearby point, say x plus delta x. So x plus delta x, value of the temperature is the known value plus delta x t dash of x plus delta x squared divided by 2 factorial t dash dash of x plus so on. And this is if we choose this point, so x, if we choose x at this point, so our x plus delta x is a point that is at a distance of delta x from it. How do we know? First of all, how do we know this x delta x? Since our length is L and we want to divide our rod into smaller sections, into smaller elements, and if the length is L and the number of elements we want to divide is, suppose we want to divide it into 5 elements, and the length L is suppose 1 meter, which means our h or our delta x is equal to total length divided by number of elements. Total length is 1 meter, number of elements are 5, which means 0.2 meter is our delta x. It's our delta x. So if we know value at x, then the value at delta x is given by this equation from the Taylor series. Now if we know the value at x, the value at the previous point, which means the x minus delta x, can be calculated again in the similar way. X minus delta x, this value will be from the theorem, it is t of x, then minus delta x t dash of x, then plus delta x squared by 2 factorial t dash dash of x, plus so on. The difference between the two is the second equation is alternatively positive negative, and this is positive negative, this positive, and second term is negative again. Now let's call them equation 1 and equation 2. What we want to do is we want to add the two equations. Why add? Because this is plus, this is minus. D dash of x will get cancelled with the t dash of x. So what we are left with is t dash dash of x. This is what we need. We need t dash dash of x. So we will be adding this. If we need t dash of x, what we will do is we will subtract them. So this will get, positive terms will get cancelled, and we will be left with t dash of x. So what we will do is we will add them. So adding equation is 1 and 2. So what if when we add these two equations, so what we'll get is t of x plus delta x plus t of x minus delta x is equal to, these two will get add up, so 2 times t of x, these two will get cancel out, then these two will get add up, so 2 factorial is 2, delta x square by 2 plus delta x square by 2 is delta x square t dash dash of x plus dot dot dot. Now what we will do is, now we want to calculate the value of t double dash of x. What we get is delta x square t dash dash of x is equal to t of x plus delta x plus t x minus delta x, and we'll transfer this term to the other side, minus twice t of x. Now we will divide both sides by delta x square. What we get is t dash dash of x equals t of x plus delta x plus, or we'll write the minus term first, minus twice t of x plus t of x minus delta x divided by delta x square. Now this is our equation. Now this is the equation where we can replace t dash dash of x, the second derivative term, with this right hand side. Now if we focus on the right hand side, there is no derivative term, there is no differential form, it is just functional form t, there is no t dash or t double dash, which means this is a function where we can, this is the function which converts a differential equation into an pure algebraic form of the equation. This is the finite difference method, is one of the way where we can convert a differential equation into an algebraic equation, and that algebraic equation is solved for each element to get the solution. This is our function which we want to solve, and we know we can replace this now. We can replace this by the finite difference method by t of x plus delta x minus twice t of x plus t of x minus delta x divided by delta x squared equals 0. Now we can multiply both by delta x square, and what we are left with is tx plus delta x minus twice t of x plus t of x minus delta x equals 0. So we converted our differential equation into an algebraic equation. So what we did is basically differential equation we converted into algebraic equation. We converted into algebraic equation, which is basically the finite difference formula, which we call it finite difference representation. So we have a differential equation, then we have its solution as t x plus delta x minus 2tx plus x minus delta x divided by delta x squared plus plus something, because we ignore the higher order terms. We ignore in the series expansion that was continuing and that was going to infinity. So we we neglected the higher order terms. Suppose if we consider those higher order terms as well, so there will be plus something. So this is our differential equation. This is called finite. This is called finite difference representation or formulation. This is finite difference formulation, and whatever we neglected is called truncation error. Truncation error. This is our differential equation. It is equal to the finite difference formula plus the truncation error. So this is the exact value of our differential equation. Exact value. If we consider this as well as the truncation error, we will get the exact value of the finite difference, of the differential equation. But if we ignore the truncation error, so our differential equation will have the approximate value, not the exact value, which is given by x plus t of x plus delta x minus twice t of x plus t of x minus delta x divided by delta x square. So this will be the whatever value we get, that will be the approximate value of the second order differential equation, or whatever the differential equation is if we ignore the truncation error. So the finite difference representation is this, and this will give us the approximate value, and how approximate or how accurate this value will be depends on the how many elements we are taking. If we take the more number of elements, the accuracy will be higher. If we take lesser number of elements, the accuracy will be lower. It depends on that. So moving forward, we have our rod. This is 100, this is 20 degrees Celsius, and suppose there are, how many elements we are choosing? 1, 2, 3, 4, 5. Suppose that we are choosing 5 elements here, and this is one point, another point, another point, another point, this point, and this point. At point 1, the value we know, T1 is this, and 2, 3, 4, 5, 6, and point 6, the value is 20 degrees Celsius. We want to find T2 to T5. We want to calculate these values. Then those values will be tabulated, which is our numerical solution finally. Now these points are called nodes. Or we call them grid points. Nodes or grid points. So what we did is we divided the domain. We divide the entire domain into some number of elements depending upon how much accuracy we want. So let's, for the example, we divided into 5 elements, and there will be obviously 6 nodes. Now how we'll do that is, now let us convert this equation into like a number form. Let us give the subscripts 1, 2, and 3. Suppose this is T1 minus 2 times T2 plus T3 is equal to 0. Suppose this is the general form of the equation that we will remember for this. Now applying this equation to point 1, 2, 3, 4, 5, 6. So for first 3 pointers, T1 is 100 minus twice T2 is unknown plus T3 is unknown. This is our first equation. We cannot solve it. This is one equation and there are 2 unknowns. Now for the second point, this will become T2. For the second point, this will become T2. This will become T3. This will become T4 is equal to 0. So neither 2 nor 3 nor 4 is known. So this is our second equation. There are 3 unknowns. Now for the next point, this will become T3 minus 2 times T4 plus T5 equal to 0. This is our next equation. And there is still 6th point. So T3 will become T4. So T4 minus 2 times T5 plus T6 is equal to 0. And we know T6 is known. It is 20. So we can put 20 here. 20 here. So we have 1, 2, 3, we have 4 equations, and we have 1, 2, 3, and 4 unknowns. So 4 equations, 4 unknowns, we can solve them using like say Gauss elimination method or whatever method, we have four equations, four variables we can solve using any method, and we can get the value of unknowns 2, 3 and 4. We'll tabulate them. We did not get any analytical, so we did not get solution in the form of function, and based on that function if we had gotten that analytical function somehow, this is 0, this is say whatever length of the rod is L, using that analytical function we could have put any value of x and we would have gotten any value of t. But since no such analytical solution exists, only the numerical solution exists, we chose this type of elements. We got these type of nodes inside, say 4 nodes inside, and we will get the numerical solution on these 4 nodes only, at this and this, say. So if we wanted value somewhere here, that means we have to we have to divide this domain into more number of elements, say 1, 2, 3, 4, 5, 6, 7, 8, and in such a way we have to divide this domain, divide it into those number of elements for which one of the discrete point will be exactly at our desired point where we want the solution. So finally we will have our x values, we will have our t values, and we will get the solution in the tabulated form. And this is what is numerical solution, and this is how we use the finite difference method to solve a differential equation and get the numerical solution. Now, since we are studying basically the COMSOL multiphysics, and COMSOL multiphysics uses the similar idea, but it does not use the finite difference method. COMSOL multiphysics, as I said last time, it uses the finite element method. It uses finite element method for the differential equations, which depends upon spatial differential equations. It uses finite element method, and for the differential equations which depends on time, there is a, for example, if we see the heat conduction equation of the Fourier, it is second order in space and it is first order in time. That means it depends on space as well as time. Second order in space, it will use finite element method to solve that part, that domain, spatial domain, and it will use the backward differentiation method. A formula. It uses backward differentiation formula BDF for time domain. So for solving the time part of that differential equation, it uses backward differentiation formula, and for the spatial domain, it uses the finite element method. We are not going into those kinds of things. We are dealing with directly with the software, how to use it, and I am giving this the background in order to understand the basic terminology that will be used in understanding that software. What is discretization, which basically I wanted to teach here, is what is discretization and meshing. Where does these two terms fit in all of this? So first of all, let us start with discretization. Discretization means to make something is continuous, to make it not continuous is to discretize it. In simple words, what does that mean? Suppose we had a solution rod. Suppose we had a rod, and it is temperature distribution inside at any point would have been given by analytical solution. Now that solution is not possible for some type of equations, like I said that I told about the cos of x square. It's not possible, so there is no closed form of solution. So what we do is we use a numerical solution, as I explained. Numerical solution, and we know that numerical solution is not available at any point continuously at any point in the domain. It is available for the selected points in the domain depending on how we divide the domain. It's available at discontinuous pointers, at selected pointers, in other words at discrete pointers. So this is known as dividing the domain into discrete points, dividing the entire domain solution into discrete pointers. This process is called a discretization. This process is called discretization. Now discretization is of two types. Suppose differential equation, say alpha dou t by dou t plus del of mu del t something like is equal to 0. A random differential equation I took. It has the time part and it has the special it has the derivative part. This del, we know del is dou by dou x plus dou by dou y plus dou by dou z. So this is the spatial part, means it depends on spatial coordinates, and this is the time part, depends on time coordinates. So this is defined in spatial domain. Spatial domain means domain that has x axis, y axis, z axis. So this part we are solving. We are solving in spatial domain, the domain that has coordinates, and this part we solve in time. So time domain. This is called time domain. Now, as I said, COMSOL uses finite element method to solve the spatial part of the differential equation in spatial domain, and it uses backward difference formulation to solve the time dependent part of the equation in the time domain. Now for the solution we have to discretize time domain and we have to discretize the spatial domain. Both we have to discretize and solve in the similar way. One part solved by FEM despite discretizing the domain, another part solved by BDF by discretizing the time domain. Now both discretizations, both terms when discretized, we give them name the discretization. Time discretization, spatial discretization. Time discretization, and here domain discretization or spatial discretization. This part is called spatial discretization. Now spatial discretization is also known as meshing. Spatial discretization is also known as meshing. So when a spatial domain is divided into selected number of nodes, selected number of elements, and get the solution in the numerical form, in the tabulated form, that discretization is called meshing. Now meshing has different types. There are different types of meshing. Now let's move to the types of meshing. Now meshing. So if that spatial domain is one dimensional, like we studied in class 11, 12, high school physics or mathematics, we say this is x, this is y, and there is some function, say y is equal to f of x, and we know that this function has domain, suppose from this to this, as it ends here, it starts here, say it has domain this is A, this is B, and the x is defined from A to B, so this is the domain of this function. We know this. Now we know this domain is one dimensional. This is 1D, one dimensional domain. That means when we discretize one dimensional domain, so its element will be obviously line segment. Each element will be line segment. Now if we have a function that is defined in function in two variables, so function in two variables will be something like this. This is x axis, this is y axis, this is z axis, and this is the function in two variable. And we know function in one variable represents a curve, and function in two variable represents a surface. Suppose this is that surface which function in two variable represents, means z is equal to f of x comma y. Now we know for this surface the domain is not line. The domain will be some area. This will be its domain. So this part is its domain. So here domain is two-dimensional. So when domain is two-dimensional and when we discretize this two-dimensional domain, each element is either triangle triangle, or it can be any quadrilateral. It can be any quadrilateral. Accordingly, this type of meshing is known as triangular meshing, or whatever the quadrilateral type is, that type of meshing. Now if we move to, suppose if our function is something like w is equal to f of x comma y comma z. We know one variable curve in 2 dimension, 2 variable surface in 3 dimension. This is basically a graph in 3 dimension. Now if we include one more variable, that will be some 3-dimensional shape in 4-dimensional space. So we cannot show that on board, or even not here. So this is basically a graph in space where we have x-axis, we have y-axis, we have z-axis, and this is a surface that is floating in space. Now we're adding another variable with the shape will be 3-dimensional, something like sphere or any 3-dimensional shape, but in 4-dimensional space, which cannot be shown. So for those kinds of functions, which are basically 3-dimensional function, for those kinds of functions, the domain is here, the domain is line. Here the domain is 2-dimensional. For those type of functions which depends on 3 variables, so domain is basically 3-dimensional domain. 3-dimensional domain. And when we domain is 3-dimensional, so when we discretize, when we divide that 3-dimensional domain into smaller elements for the discretization purpose, each element will be a 3-dimensional element. So that is either suppose tetrahedra, or suppose hexahedra, depending upon the shape of each element we choose. So accordingly, these are different types of meshing: triangular meshing, quadrilateral meshing, or whatever, tetrahedral meshing. These are the names that we see in the softwares, or we hear related to the numerical solution, or related to the modeling and simulation softwares. Now there are, say, also one term is used, is called adaptive meshing. What does it mean is, suppose we have a system that we want to solve, we have a model that we want to solve, and we know before solving we have to, in order to solve this, we have to discretize the domain, we have to convert it into different number of elements, and more number of elements means we have to solve the differential equation, we have to convert it into algebraic equation, and more number of these nodes means more number of algebraic equations that we converted the differential equation into. That means we have to solve that algebraic equation, at more number of node pointers, and solving at more number of node pointers, which means that we have to solve it more number of times, which is more time consuming, which will consume more memory. That means such type of problem should be solved in the computer which have more power, high performance computers and all that. So when trying to solve a problem, we want to do the simplest meshing as possible. Suppose that's why another type of meshing goes something like coarser meshing and finer meshing. No, suppose if we divide the domain into larger elements, means lesser number of elements, because each element has a larger size, so there will be entire domain will be divided into lesser number of elements. So that type of meshing is known as coarse meshing or coarser meshing. And for coarser meshing, there will be number of elements will be less, which means less number of times this algebraic equation has to be solved, which means less time consuming, and a quick simulation time will be less. But if we take more number of elements, that means if we take the finer mesh, that means more number of node pointers, and we have to solve that algebraic equation. The computer has to solve that algebraic equation at more number of pointers, means more number of times, which means time consuming and requires more memory and high performance. Now the question arises, when to use coarser mesh and when to use finer mesh. Now that depends on the problem. Suppose if we have a problem where, if we suppose talk about our temperature on the rod, suppose if the temperature is varying smoothly, if this is the temperature variation inside the rod, then choosing coarser mesh will also give us the solution. because this for this element the solution will be like this straight line, for this element it will be like this straight line, for this straight line, this straight line, this straight line, this straight line, and we'll combine all these pieces of lines during integration and we'll get this final solution like this. But if the temperature varies something like this, sharply it increases, decreases, so choosing this size of element will not capture this gradient detail. The temperature gradients are high, the temperatures are varying sharply. That means choosing this large element will not capture this detail. It will give some variation, some uniform variation. For each element it gives us uniform solution, so it will not capture. So we have, in order to capture each detail, we have to further divide it into smaller elements so that it captures all the details. So when a property inside a system varies sharply, varies largely, there are larger property gradients, temperature gradients, pressure gradients. In the region where the property gradients are large, we use finer mesh, and in the region where property is not changing sharply, it is smoothly varying, so we can take the coarser mesh in those parts. So we have to, so when we solve in a computer, we make the model of the system, then it will have different domains, like this side is considered one domain, this side is considered another domain, top side another domain. Likewise it will have different domains, and if we know that in the front domain the temperature is varying sharply, the temperature gradients are high, for this domain we will select the finer mesh. And if we say top domain, the top side where temperature is not varying that much, so we can choose a coarser meshing for that part, for that domain. And for different parts we can choose different types of meshing. And also there is something called adaptive meshing, which computer itself decides which part has high gradients, and it itself adjusts and chooses the finer meshing. It uses the finer meshing in those areas, and in other areas where gradients are not high, it chooses the coarser meshing. Itself decides, it itself adapts according to the problem and gives us the optimal solution, gives the solution in the most optimal way. So this was all about what is meshing and what is discretization, and all it started with the numerical solution. And this is how we solve a function which cannot be solved analytically. This is how we solve it numerically, and this is when solving it numerically, this is how these different concepts come in, and this is how we approach to the concept of meshing and what are its various types. This episode was needed to elaborate one of the steps in solving a problem in COMSOL, and that was meshing. Thank you.